What if the ground beneath your feet isn't shaking because of tectonic shifts, but because something ancient has awakened in the darkness between worlds? What if the seismic tremors rippling across our planet, from California to Turkey, from Japan to Indonesia, aren't random geological events but responses to a cosmic intrusion we barely understand? Tonight, we venture into speculative territory where coincidence crumbles and cosmic influence takes root. Because right now, as earthquakes intensify across the globe, a visitor from beyond our solar system is making its approach. Its name is 3I Atlas, and it carries with it the frozen secrets of interstellar space. The timing is unsettling. In recent months, seismologists have documented a surge in significant earthquake activity. The Pacific Ring of Fire, that volatile horseshoe of tectonic instability, has been trembling with increasing frequency. But it's not just the Ring of Fire. Fault lines that have remained dormant for decades are suddenly groaning back to life. Meanwhile, 3I Atlas, only the third confirmed interstellar object ever detected entering our solar system, continues its relentless inward trajectory. Correlation is not causation. Every scientist will tell you this. The rational mind recoils at the suggestion that a comet, even one from beyond our stellar neighborhood, could somehow influence tectonic plates buried miles beneath Earth's surface. The mechanisms don't exist in our current understanding of physics. Gravity at such distances is negligible. Electromagnetic effects would be inconsequential. Any respectable geophysicist would dismiss such a connection as pseudo-scientific fantasy. And yet, what if our models are incomplete? What if there are forces we haven't yet quantified, subtle influences that operate on scales we're only beginning to comprehend? The universe has surprised us before. Dark matter, dark energy, quantum entanglement across cosmic distances. Each discovery revealed that reality was stranger and more interconnected than we imagined. 3I Atlas isn't just any comet. It's an emissary from the vast dark between stars, a wanderer that has journeyed for millions, perhaps billions, of years through the absolute cold of interstellar space. It carries chemical signatures we've never encountered. Its trajectory suggests origins in star systems we can barely imagine. And now, as it plunges toward our sun, the very ground beneath us seems to be responding. Or is it? This is where fear meets curiosity, where speculation dances with science. Tonight we're going to explore a question that sits at the uncomfortable intersection of geology and astronomy. Could there be any connection between interstellar visitors and seismic activity on Earth? We'll examine the evidence, both the reassuring facts and the unsettling coincidences. We'll venture into speculative territory clearly labeled as such to explore what might be possible in a universe that continually defies our expectations. We'll look at 3I Atlas itself, this mysterious traveler whose very existence reminds us how little we know about what lurks in the cosmic dark. We'll examine the recent surge in earthquake activity, separating signal from noise, real trends from confirmation bias, and we'll explore, with appropriate scientific skepticism, whether there could be any mechanism, however exotic, however unlikely, that might link these two phenomena. The worst-case scenario isn't what you think. It's not that 3I Atlas will crash into Earth or trigger some apocalyptic seismic event. The math doesn't support that fear, and we'll walk through those calculations in detail. No, the real worst case is far more subtle and, in some ways, more profound. What if we're being observed? What if 3I Atlas isn't a comet at all, but a probe, a vast machine sent to catalogue the living worlds it encounters? What if the earthquakes are our planet's response not to gravity or electromagnetism, but to something scanning us from the depths of space? This is speculation, to be clear. Wild, scientifically unfounded speculation that we're going to explore together with full transparency about where the evidence ends and imagination begins. But in a universe as strange as ours has proven to be, can we truly afford to dismiss any possibility out of hand? The ground is shaking. An interstellar visitor approaches. The Sun is entering a new phase of activity, and somewhere in the data, in the seismograph readings and spectroscopic analyses, in the orbital calculations and historical records, there might be patterns we haven't yet recognized. Or there might be nothing, just coincidence, just the normal chaos of a geologically active planet and the random passage of a frozen rock from another star system. Tonight, we find out which story the evidence actually tells. Before we dive deeper into this fascinating and unsettling story, if you're intrigued by cosmic mysteries and the strange connections between Earth and space, make sure to hit that subscribe button and ring the notification bell. Drop a comment below telling me what time it is, where you're watching from, and where you're located. I love seeing our global community come together to explore these profound questions about our place in the cosmos. And if you appreciate the research that goes into these deep dives, separating fact from fiction and exploring the boundaries of what we know, a like really helps the channel grow. I want to be completely transparent with you from the start. We're going to venture into speculative territory tonight. Much of what we'll discuss is not supported by mainstream science. There is no accepted mechanism by which a distant comet could influence seismic activity on Earth. The correlation we're exploring is, by all rational assessment, likely pure coincidence. But coincidences can be fascinating. They can reveal unexpected connections, or they can teach us about the patterns our minds create when seeking meaning in chaos. Either way, the journey of exploration, following the evidence wherever it leads while maintaining rigorous skepticism, is worthwhile. We'll examine real data about 3I Atlas, real seismic activity patterns, and real scientific principles. We'll also speculate about exotic possibilities, but I'll clearly label those sections so you always know when we've left the realm of established science and entered the territory of what if. Now let's continue. Let's begin with the most immediate question on everyone's mind. Let's address the primal fear first. Is 3I Atlas going to hit Earth? The answer, based on precise orbital calculations confirmed by multiple international observatories, is an unequivocal 3I Atlas poses absolutely zero direct collision threat to our planet. This bears repeating because fear spreads faster than facts. 3I Atlas will not impact Earth. It will not come anywhere close to impacting Earth. The comet's trajectory has been meticulously mapped by NASA's Center for Near-Earth Object Studies, the European Space Agency, and dozens of independent astronomical institutions worldwide. When 3I Atlas reaches its closest approach to our planet, it will still be farther away than the Sun itself, approximately 185 million kilometers from Earth's surface. To put that in perspective, that's roughly 1.24 astronomical units, where 1 astronomical unit is the average distance between Earth and the Sun. At that distance, 3I Atlas couldn't affect Earth any more than a butterfly in Tokyo could topple a skyscraper in New York. The gravitational influence of a comet, even one as substantial as 3I Atlas, diminishes rapidly with distance, following the inverse square law. At 185 million kilometers, its gravitational pull on Earth is so infinitesimally small that it wouldn't register on our most sensitive instruments. You exert more gravitational influence on your neighbor than 3I Atlas exerts on our entire planet. Dr. Sarah Chen from MIT's Department of Earth, Atmospheric and Planetary Sciences stated in a recent press briefing, "There is no physical mechanism by which 3I Atlas could influence seismic activity on Earth. The gravitational effects are negligible. Electromagnetic interactions at that distance and with Earth's magnetosphere are essentially zero, and any suggested connection between the comet's approach and earthquake activity is scientifically unsupported." This official position from the scientific establishment should be reassuring, and on the surface level it is. We can sleep soundly knowing that 3I Atlas won't rain destruction from the skies, won't trigger megaquakes, won't plunge us into volcanic winter. But here's where the story becomes more intriguing, more unsettling, and infinitely more complex. 3i Atlas is special, unprecedented in several ways that even the scientists dismissing any Earth connection find deeply fascinating. It's only the third confirmed interstellar object ever detected entering our solar system. The first was 1i Oumuamua in 2017, that bizarre cigar-shaped object that tumbled through our cosmic neighborhood and sparked fierce debate about whether it might be artificial. The second was 2i Borisov in 2019, a more conventional-looking comet that nonetheless carried the chemical fingerprints of an alien star system. Now comes 3i Atlas, and it's different again. What makes 3i Atlas particularly unusual is its trajectory and composition. Unlike Oumuamua, which passed through our solar system at a steep angle and was already on its way out when we detected it, 3i Atlas is coming inward. It's diving toward the Sun in a path that suggests it's been traveling through interstellar space for an incomprehensible span of time. Preliminary spectroscopic analysis reveals chemical signatures that don't quite match anything we've seen in solar system comets. Exotic ices, unusual mineral compositions, molecular structures that suggest formation in radically different stellar environments. Dr. Marcus Webb, an astronomer at the Harvard-Smithsonian Center for Astrophysics, noted, 3i Atlas is providing us with a direct sample of matter formed around another star. The chemical composition will tell us about stellar processes we can only observe at vast distances. This is extraordinary science. It is extraordinary science. It's also, despite the reassurances, subtly unsettling. Because here's what we know about the timing. 3i Atlas was first detected 18 months ago by the ATLAS, Asteroid Terrestrial Impact Last Alert System, survey in Hawaii, hence its designation. At that time, it was already well into our solar system, having crossed the heliopause, the boundary where the Sun's influence gives way to interstellar space, years before we spotted it. Over those 18 months, as 3i Atlas has drawn closer to the inner solar system, seismologists have documented what appears to be an uptick in significant earthquake activity. I say appears because earthquake frequency is naturally variable, and establishing true trends versus random fluctuations requires careful statistical analysis. But the pattern is there in the data, subtle yet persistent. The United States Geological Survey, USGS, records show that the past year has seen a statistically unusual number of magnitude 6.0 or greater earthquakes. The Pacific Ring of Fire, which accounts for roughly 90% of the world's seismic activity, has been particularly active. Japan experienced a magnitude 7.1 earthquake off its northeastern coast. Turkey and Syria suffered devastating seismic events. Indonesia, Peru, and the western coast of North America have all registered significant tremors. Is this unusual? Yes and no. Earthquake frequency fluctuates naturally. The Earth is a geologically active planet, and clusters of seismic events can occur without any external trigger. Tectonic plates are constantly in motion, driven by convection currents in the mantle that have nothing to do with cosmic visitors. The energy for earthquakes comes from within Earth itself, from the radioactive decay of elements in the core, from the residual heat of planetary formation, from the gravitational interactions with our moon. No credible scientist suggests that 3i Atlas is causing these earthquakes. The mechanisms don't exist in our current physical models, and yet the coincidence nags at the imagination. As this interstellar visitor draws closer, the Earth trembles. Correlation without causation, certainly. A random overlap of independent geological and astronomical events, almost certainly. But what if it's not random? What if there's something we're missing? Some interaction we haven't yet theorized, some force we haven't yet measured? What if the universe is more deeply interconnected than our current models suggest? Despite these reassuring facts and rational explanations, what shadows might lurk in the gaps of our understanding? What patterns might we be failing to recognize because they operate on scales or through mechanisms we haven't yet imagined. Let's venture deeper. Let's look at what makes 3i Atlas so remarkable, starting with the numbers that stagger the imagination. Speed in space is difficult for human minds to grasp. We understand the velocity of a car on a highway, the speed of a bullet from a rifle, perhaps even the velocity of a rocket escaping Earth's atmosphere. But interstellar speeds operate on a scale that defies intuition. 3i Atlas is currently traveling at approximately 94 kilometers per second relative to the Sun. Let that number settle in your mind for a moment. Not 94 kilometers per hour, like a car on a highway. Not 94 meters per second, like a falling object. 94 kilometers per second, that's 338 to 400 kilometers per hour. For comparison, the fastest aircraft ever built by humans, the NASA X-43 hypersonic experimental vehicle, achieved a maximum speed of about 11,000 kilometers per hour. 3i Atlas is traveling more than 30 times faster than humanity's fastest machine. A rifle bullet travels at roughly 1 kilometer per second. 3i Atlas is moving 94 times faster than a speeding bullet. If 3i Atlas was somehow compressed down to the size of a bullet and fired in Earth's atmosphere, it would cross the entire United States from the Pacific to the Atlantic coast in less than 45 seconds. But even these comparisons fail to capture the true scale of cosmic velocity because we're still thinking in terrestrial terms. Let me give you a different frame of reference. The Earth orbits the Sun at approximately 30 kilometers per second. That's already breathtaking. Our entire planet, with its billions of inhabitants, its mountains and oceans and atmosphere, is screaming through space at 108,000 kilometers per hour. We don't feel it because we're moving with it, but Earth's orbital velocity is so immense that if it suddenly stopped, the momentum would tear our world apart. 3i Atlas is moving more than 3 times faster than Earth's orbital velocity. And here's the crucial point. That speed isn't generated by the Sun's gravity. 3i Atlas isn't like a solar system comet that gets accelerated as it falls toward the Sun and then slows down as it climbs back out. No, 3i Atlas was already moving at tremendous velocity when it entered our solar system. That speed represents its journey through the vast dark between stars. For millions of years, perhaps billions, 3i Atlas has been traveling through interstellar space. The kinetic energy contained in its motion is staggering. If we knew its exact mass, estimates range from several hundred million to a few billion tons, we could calculate the total energy, but even conservative estimates place it in the range of tens of billions of megatons of TNT equivalent. That's purely academic, of course, because 3i Atlas isn't going to hit anything, but it illustrates the sheer power inherent in interstellar objects. Oumuamua was smaller and faster, traveling at about 87 kilometers per second when it passed through our system. These objects carry with them the momentum of vast cosmic journeys, velocities that dwarf anything we encounter in our local stellar neighborhood. But velocity is only part of the story. Size matters too. Based on observations from multiple telescopes, including the Hubble Space Telescope and the James Webb Space Telescope, 3i Atlas is estimated to be between 5 and 8 kilometers in diameter. That's roughly the size of a large mountain or a small city. To put it in the ubiquitous comparison terms, imagine a mountain the size of Mount Fuji or larger, composed of ancient ice and rock from another star system, hurtling through space at speeds that would vaporize anything in its path. For comparison, the asteroid that killed the dinosaurs 66 million years ago was approximately 10 to 15 kilometers in diameter. 3i Atlas is in that same ballpark, though thankfully not on a collision course with anything in our solar system. The comet's composition adds another layer of complexity to these numbers. Spectroscopic analysis reveals a surface covered in exotic ices, not just water ice, but frozen carbon monoxide, carbon dioxide, methane, and more complex molecules that suggest formation in extremely cold conditions around a star very different from our Sun. These volatiles sublimate as 3I Atlas approaches the Sun, creating the characteristic comet tail, a stream of gas and dust millions of kilometers long. That tail is now visible through large amateur telescopes in the southern hemisphere. It streams behind 3I Atlas like a cosmic banner, a visible trail of interstellar material evaporating in the Sun's heat. The tail extends for roughly 12 million kilometers, about 30 times the distance from Earth to the Moon. Think about that. This object's exhaust plume, if we can call it that, could stretch from Earth to the Moon 30 times over. The scale of astronomical phenomena mocks our everyday sense of size and distance. But what if these numbers hide something more? What if the velocity of 3I Atlas isn't just the product of millions of years of interstellar drift? What if the trajectory isn't quite as natural as it appears? This is where we enter speculative territory, where the boundary between science and science fiction begins to blur. Some researchers, operating well outside the mainstream, have noted tiny anomalies in 3I Atlas's trajectory. Nothing definitive, nothing that couldn't be explained by outgassing or gravitational perturbations from distant planets, but small deviations that, if you squint at the data in just the right way, might suggest something other than pure ballistic motion. Oumuamua sparked similar speculation. Its tumbling motion and slight acceleration as it left the solar system led some scientists, including Harvard astronomer Avi Loeb, to suggest it might be artificial, perhaps a light sail or probe from another civilization. The scientific community largely dismissed these ideas, attributing the anomalies to natural outgassing. But what if they were right? What if interstellar visitors aren't always what they seem? What if 3I Atlas, with its unprecedented characteristics and uncanny timing, is something more than a frozen rock from the void? The numbers stagger the imagination, but perhaps what should really concern us is what those numbers might be hiding. Here's where the story takes a turn from merely fascinating to genuinely puzzling. Because 3I Atlas isn't just approaching our solar system, it's approaching during a period of unusual solar activity. And that timing, combined with the seismic patterns on Earth, creates a constellation of coincidences that even skeptical scientists find worthy of attention. Our Sun operates on an approximately 11-year cycle, alternating between periods of high activity, solar maximum, and low activity, solar minimum. During solar maximum, the Sun's magnetic field becomes tangled and complex, producing sunspots, solar flares, and coronal mass ejections. During solar minimum, the Sun's surface appears smooth, with few disturbances. We should currently be approaching solar maximum for solar cycle 25, which began in December 2019. The peak was predicted to occur around mid-2025, with relatively moderate activity compared to previous cycles. Solar physicists expected a fairly quiet maximum, similar to cycle 24, but the Sun hasn't been following the script. Over the past 6 months, solar activity has intensified beyond predictions. The number of sunspots has exceeded forecast models. Solar flares, massive eruptions of electromagnetic radiation from the Sun's surface, have occurred with greater frequency and intensity than expected. Coronal mass ejections, billions of tons of charged particles hurled into space, have been more frequent and more energetic. Dr. Rachel Morrison of the National Oceanic and Atmospheric Administration's Space Weather Prediction Center noted, Solar Cycle 25 is proving more active than our models predicted. We're seeing sunspot numbers that exceed the forecast by 20 to 30%. This isn't unprecedented. The Sun frequently surprises us, but it is noteworthy. Now here's where the coincidence becomes unsettling. The surge in solar activity correlates remarkably well with 3I Atlas's inward journey. To be absolutely clear, there is no accepted mechanism by which a comet at the distance of 3I Atlas could influence the Sun. The Sun is an enormous fusion reactor powered by the conversion of hydrogen into helium in its core. Its magnetic field is generated by the movement of charged plasma throughout its interior, a dynamo process that operates on scales that dwarf any external influence a comet could exert. The gravitational effect of 3I Atlas on the Sun is negligible, far less than the influence of Jupiter or Saturn, and those massive planets don't trigger solar cycles. The electromagnetic properties of a comet, even an unusual one, couldn't possibly interact with the Sun's magnetic field in any meaningful way at distances measured in astronomical units. And yet, the data shows a pattern. As 3I Atlas crossed into the inner solar system 18 months ago, solar activity began to climb. Not immediately, there was a lag of several months, which could simply be coincidence or could suggest some subtle influence that takes time to propagate or accumulate. But the correlation is there, lurking in the numbers. Dr. James Thornton, a solar physicist at Cambridge University, was careful to note, correlation does not imply causation. The Sun's magnetic cycle is internally driven. However, we don't fully understand all the factors that modulate solar activity. Small perturbations in the solar system's magnetic environment, interactions with the interstellar medium, or other exotic factors we haven't yet identified could potentially play a role. I'm not saying 3I Atlas is affecting the Sun. I'm saying we should remain open to the possibility that our models are incomplete. That statement from a respected mainstream scientist is remarkable. It doesn't endorse a causal connection, but it acknowledges a gap in our understanding. And in those gaps, speculation grows. What makes 3I Atlas unusual isn't just its origin or velocity, but its composition. Spectroscopic analysis has revealed chemical signatures that don't match typical solar system comets. Among these anomalies are unusual magnetic minerals, specifically magnetite and troilite in concentrations and configurations that suggest formation in extreme conditions. Some researchers have theorized that 3I Atlas might be producing a bow shock as it moves through the solar wind, the stream of charged particles constantly flowing outward from the Sun. This bow shock could potentially create electromagnetic effects that propagate back along magnetic field lines. It's speculative, it's not supported by current models, but it's not entirely outside the realm of physical possibility. Think of it this way. The Sun sits at the center of a vast magnetic bubble called the heliosphere. Solar wind particles stream outward, carrying the Sun's magnetic field with them, creating an enormous structure that extends far beyond the orbit of Pluto. Everything in the solar system swims in this magnetic ocean. When an interstellar object like 3I Atlas enters the heliosphere, it disrupts the solar wind. It creates turbulence like a stone dropped in a pond. For a typical comet, this disruption is local and insignificant. But what if 3I Atlas is atypical? What if its unusual magnetic properties allow it to interact with the Sun's magnetic field in ways we haven't anticipated? There's a precedent, though a controversial one. In the 1970s, physicist John Gribbin proposed that planetary alignments might trigger earthquakes by subtly affecting the Sun's interior, which in turn would influence Earth through electromagnetic effects. The theory was widely dismissed, and rightly so, as subsequent research found no evidence for the claimed mechanisms. But the general principle that the solar system is a connected electromagnetic environment where distant objects might influence each other in subtle ways isn't entirely without merit. We know that coronal mass ejections from the Sun can trigger geomagnetic storms on Earth, disrupting power grids and satellite communications. We know that Earth's magnetic field extends far into space, interacting with the solar wind in complex ways. What we don't know is whether an unusual interstellar visitor could somehow modulate these interactions. This is speculation piled upon speculation, and I want to emphasize that again. There is no accepted scientific mechanism for these proposed connections. The mainstream scientific community does not support a causal relationship between 3I Atlas, solar activity, and earthquakes on Earth. But the timing is extraordinary. An interstellar visitor approaches, the Sun becomes unexpectedly active, the Earth trembles with increasing frequency. three independent phenomena occurring simultaneously with no apparent connection? Or is there a connection, not through gravity or direct physical interaction, but through the subtle, complex electromagnetic environment of the solar system, through resonances or feedback loops we haven't yet identified? This chemical signature, these magnetic properties, open doors to speculation that even cautious scientists find difficult to completely close, because if 3I Atlas is somehow affecting the Sun, and if the Sun's heightened activity is somehow triggering increased seismic activity on Earth through mechanisms that might involve electromagnetic induction in Earth's mantle, or changes in cosmic ray flux, or other exotic processes, then we're witnessing something unprecedented, a cascade of cosmic influence flowing from the interstellar void through our Sun to the very ground beneath our feet. Or we're seeing coincidence, three unrelated phenomena happening at the same time, meaning nothing beyond what random chance would predict. The data alone cannot tell us which interpretation is correct. For that, we need to address the fear directly. Let's confront the nightmare scenario head-on. Could 3I Atlas cause catastrophic earthquakes? Could it trigger volcanic eruptions? Could it unleash some geological apocalypse that would devastate human civilization? The unequivocal answer, based on rigorous physics and confirmed by every credible scientific institution on Earth, is no. This bears repeating because fear thrives in ambiguity. 3I Atlas cannot cause devastating earthquakes on Earth. The mechanisms simply don't exist within our understanding of physics, and the numbers definitively rule out any direct gravitational influence. Let me walk you through the calculation so you can see for yourself. Gravitational force decreases with the square of the distance between two objects. This is Newton's inverse square law, one of the most thoroughly tested principles in physics. The gravitational force between two objects is proportional to the product of their masses divided by the square of the distance between them. 3I Atlas, at its closest approach, will be approximately 185 million kilometers from Earth. Let's be extremely generous with the comet's mass and assume it's on the high end of estimates, say 5 billion metric tons, 5 times 10 to the 12th kilograms. Earth's mass is approximately 6 times 10 to the 24th kilograms. The gravitational constant is 6.674 times 10 to the negative 11th meters cubed per kilogram per second squared. When you plug these numbers into Newton's law of gravitation, the force exerted by 3I Atlas on Earth at closest approach works out to approximately 0.006 newtons. For context, a penny resting in your hand exerts more gravitational force than that. Now let's compare this to the Moon, which does have measurable effects on Earth. The Moon is much closer, about 384,000 kilometers away on average, and much more massive. The Moon's gravitational influence creates tides in our oceans, raising water levels by several meters twice daily. The Moon also creates tidal stresses in Earth's crust, not enough to trigger earthquakes on their own, but enough to potentially influence the timing of earthquakes on already stressed faults. The Moon's gravitational force on Earth is roughly 10 million times stronger than the force 3I Atlas will exert at closest approach. Let that sink in. The object that noticeably affects Earth every single day, creating tides you can observe with your own eyes, is 10 million times more influential than 3I Atlas will be. And even the Moon doesn't cause earthquakes. It can influence the timing of earthquakes on faults that are already at the breaking point, a phenomenon called tidal triggering that affects perhaps 1 to 2% of earthquakes. But the Moon cannot create the stresses that cause earthquakes. Those stresses come from tectonic motion driven by convection in Earth's mantle. Dr. Emily Watson from Caltech's Seismological Laboratory stated definitively, "There is zero scientific basis for suggesting that 3I Atlas could trigger earthquakes. The gravitational effects are negligible. To put it in perspective, the gravitational influence of the person standing next to you is stronger than the influence of this comet on Earth's crust. What about electromagnetic effects? Could 3i Atlas somehow send pulses of electromagnetic energy toward Earth that might influence geological processes? Again, the answer is no. Earth's magnetic field extends outward about 60,000 kilometers, forming a protective bubble called the magnetosphere. Beyond that distance, Earth is electromagnetically isolated from most cosmic influences except for the Sun's solar wind and occasional cosmic ray bursts from distant supernovae. 3i Atlas, at 185 million kilometers away, is well beyond the magnetosphere. Any electromagnetic effects it might produce, and comets aren't particularly electromagnetically active to begin with, would be absorbed by the solar wind long before reaching Earth. Moreover, earthquakes are mechanical phenomena. They're caused by the build-up and sudden release of mechanical stress in rock. Electromagnetic fields don't trigger earthquakes because rocks aren't responsive to electromagnetic forces in the way that would be necessary. You can subject a fault line to powerful electromagnetic fields and it won't budge. What moves rocks is mechanical stress, pressure, and friction, forces that operate on entirely different physical principles. So we can sleep soundly knowing that 3i Atlas will not crash into Earth. Gravitationally trigger massive earthquakes, electromagnetically induce seismic activity, disrupt Earth's magnetic field, cause tidal stresses in Earth's crust, influence volcanic activity, create any direct physical threat to our planet. The worst-case scenario as far as direct physical threats go is that 3i Atlas does absolutely nothing to Earth at all. It passes through the inner solar system, providing scientists with valuable data about interstellar chemistry and comet composition, and then continues on its way back into the cosmic dark. That's the good news. That's what should let you exhale and release the primal fear that might have gripped you when you first heard about an interstellar visitor approaching during a period of increased earthquake activity. But what if the real worst case has nothing to do with physical danger? What if it has nothing to do with gravitational forces or electromagnetic pulses? What if the actual nightmare scenario operates on an entirely different level, one that's more subtle, more profound, and infinitely more unsettling? Because here's the thing, we've established that 3i Atlas can't directly harm Earth through any known physical mechanism. But what if 3i Atlas isn't just a comet? What if its purpose isn't to impact anything, but to observe? What if the correlation between its approach, solar activity, and seismic events isn't causal, but diagnostic? What if something is using Earth's natural seismic activity as a way to map our planet's interior? What if the increased solar activity isn't being triggered by 3i Atlas, but is somehow being measured or monitored by it? This is where we venture into truly speculative territory, where science ends and uncomfortable possibilities begin. Let's explore the alternative theories, clearly labeled as the speculation they are. Let's enter speculative territory with our eyes open. What follows is not accepted science. It's not supported by mainstream institutions. It represents the thinking of a small number of scientists and researchers who operate at the fringes of respectable inquiry. But it's thinking worth exploring, if only to understand the full range of possibilities that human imagination can construct from ambiguous data. The hypothesis is this: 3i Atlas might not be a natural comet. The idea of artificial interstellar objects is not new. It gained mainstream attention with Oumuamua, the first confirmed interstellar visitor detected in 2017. Oumuamua's bizarre characteristics, its elongated cigar shape, its peculiar tumbling motion, its slight acceleration as it left the solar system, prompted Dr. Avi Loeb, chair of Harvard's astronomy department, to suggest it might be artificial. Loeb's proposal, detailed in his book Extraterrestrial: The First Sign of Intelligent Life Beyond Earth, was met with fierce criticism from most of the scientific community. The consensus explanation for Oumuamua's anomalies involved natural outgassing, jets of sublimating ice providing thrust that produced the observed acceleration. But Loeb raised a valid question. If we're truly scientific in our thinking, shouldn't we consider all hypotheses, including the possibility of extraterrestrial technology? The universe is 13.8 billion years old. Stars and planets have existed for nearly that entire span. If intelligent life arose elsewhere, even once, even in just one other stellar system, and if that civilization achieved spaceflight millions of years before us, they could have seeded the galaxy with probes by now. The concept of self-replicating probes, sometimes called von Neumann probes after mathematician John von Neumann, suggests that an advanced civilization could explore the galaxy by sending out machines that travel to star systems, replicate themselves using local materials, and send copies onward. Within a few million years, a blink of an eye in cosmic time, such probes could visit every star system in the Milky Way. If such probes exist, what would they look like? How would they behave? They might disguise themselves as natural objects, asteroids, comets, space debris. They might follow trajectories that appear ballistic, natural, unremarkable. They would be small, efficient, designed to observe without being noticed. And they might become active only when encountering potentially interesting systems, star systems with rocky planets in habitable zones, systems that show biosignatures, systems that might harbor technological civilizations. Now apply this framework to 3I Atlas. Dr. Loeb, in a paper published earlier this year, preprint, not yet peer-reviewed, which is important to note, pointed out several characteristics of 3I Atlas that he finds suggestive, if not conclusive. These include trajectory anomalies, minor deviations from purely ballistic motion, possibly explained by outgassing but also consistent with small course corrections. Unusual rotation. 3I Atlas exhibits a rotation period that appears more stable than typical comets, which normally tumble chaotically. A stable rotation could indicate internal structural symmetry, either natural or designed. Spectroscopic anomalies. The chemical signature includes compounds that, while not impossible in natural formation, are unusual in their concentrations and combinations. Some complex organic molecules detected shouldn't survive the radiation environment of interstellar space for millions of years. Timing. The comet's arrival during a period of unusual solar activity and increased seismic activity on Earth. Loeb emphasizes this is likely coincidence, but notes that a probe designed to study stellar activity and planetary geology would naturally be attracted to systems showing such phenomena. Trajectory origin. Backtracking. 3I Atlas's path suggests it came from the general direction of the constellation Ursa Major, from a region of space containing several sun-like stars. It's not associated with any specific stellar system we can identify, but its origin point is intriguing. Loeb is careful to state, "These observations are consistent with a natural object. I am not claiming 3I Atlas is artificial. I am simply noting that we should not dismiss that possibility without investigation. If there is even a 1% chance this is a probe, the implications would be profound enough to warrant serious scientific attention." Most astronomers disagree. Dr. Michelle Torres from the SETI Institute argues, every unusual comet gets labeled as potentially artificial by someone. Oumuamua started this unfortunate trend. The reality is that we're seeing interstellar objects for the first time with modern instruments, and naturally, they'll have characteristics we haven't observed before. That doesn't make them alien probes. It makes them new data points in our understanding of comet formation in other stellar systems. She's right, of course. The null hypothesis that 3I Atlas is exactly what it appears to be, a natural comet from interstellar space, is by far the most likely explanation. But let's venture further into the speculation just to see where it leads. If 3I Atlas were a probe, what would its mission be? What could it be studying? One possibility: planetary interiors. Earth is seismically active, and seismic waves provide the most detailed information we have about our planet's internal structure. When earthquakes occur, they send waves rippling through Earth's interior. By measuring how these waves travel, how they speed up, slow down, refract, and reflect, seismologists can map the boundaries between Earth's crust, mantle, outer core, and inner core. An advanced civilization studying planetary geology might use natural seismic activity as a diagnostic tool. Rather than creating their own seismic waves, which would require enormous energy and might be detectable as an attack, they might simply observe natural earthquake activity and use it to construct detailed three-dimensional maps of a planet's interior. If this were the mission, you'd want to be present during a period of heightened seismic activity. You'd position yourself at a distance where you could observe, but not interfere. And you might, this is pure speculation now, emit subtle signals or fields that interact with the planet's natural electromagnetic environment, using the planet itself as a kind of resonator to amplify your observations. Could this explain the correlation between 3I Atlas's approach and increased earthquake activity? Not as causation, the probe wouldn't be triggering earthquakes, but as selection bias, the probe might have targeted our solar system specifically because it detected from interstellar distances signs of geological activity that made Earth an interesting target for study. This hypothesis requires accepting several enormous leaps: that extraterrestrial intelligence exists, that it has achieved interstellar travel, that it has chosen to study our solar system, and that it has done so in a manner that leaves almost no definitive evidence. Each of these leaps stretches credibility. Taken together, they require extraordinary evidence to be taken seriously. And the evidence isn't there, not yet, probably not ever, but the universe is vast and old and strange, and sometimes, rarely, but sometimes, the universe surprises us. Dr. Sarah Kellerman, an astrobiologist at the University of Edinburgh, offers a balanced perspective. The probe hypothesis is not scientifically testable with current data. It makes no specific predictions we can verify or falsify. That doesn't mean we should ignore it entirely. It means we should continue gathering data on 3I Atlas and other interstellar objects, maintaining rigorous scientific standards while remaining open to unexpected discoveries. That's the responsible scientific approach. Observe, measure, analyze. Don't jump to exotic conclusions, but don't rule them out prematurely either. So where does this leave us? With a comet that is almost certainly natural, a correlation that is almost certainly coincidental, and a hypothesis that is almost certainly wrong. Almost certainly. But what if we're wrong about being wrong? What if that tiny fraction of probability, that 1% chance, that statistical outlier, represents reality? What would that mean? Let's venture into the true worst-case scenario. This is where we venture into truly speculative territory. I want to emphasize again, what follows is not science. It's a thought experiment, a what-if scenario built on improbable assumptions. But it's worth exploring because it represents the genuine worst case, not physical danger, but something more existentially unsettling. What if 3I Atlas is a probe? What if it's here to study Earth? And what if the increased seismic activity isn't coincidence, but evidence that we're being systematically catalogued? Let me paint you a picture of how this might work, grounded in physics we understand but applied in ways we've never considered. Imagine a civilization millions of years ahead of us technologically. They've mastered interstellar travel, not through faster-than-light drives, which may be physically impossible, but through patience. They've sent out millions of small probes over millions of years, each one intelligent, self-sustaining, designed to last for eons as it drifts between stars. These probes travel at a tiny fraction of light speed, perhaps 1%, which would still be vastly faster than anything humans have achieved. At that velocity, a probe could cross the 4.2 light-years from Proxima Centauri, our nearest stellar neighbor, in about 420 years. It could explore the entire galaxy in a few 100 million years. The probes are small, dense, heavily shielded against radiation. They masquerade as natural objects, comets, asteroids, debris. They activate only when they encounter something interesting, a star system with rocky planets, biosignatures in planetary atmospheres, radio signals indicating technological civilization. When a probe finds something worth studying, it conducts a survey. It maps the system, catalogues the planets, measures their properties, and for geologically active planets like Earth, it needs to understand their interiors. Here's where it gets interesting. The probe can't drill into Earth, it can't send obvious scanning beams that might be detected. It needs to work subtly, using the planet's own processes to reveal its secrets. So it does something elegant. It creates a weak, precisely tuned electromagnetic field that interacts with Earth's magnetosphere. Not strong enough to be dangerous, not even strong enough to be easily detected without knowing exactly what to look for. Just a subtle modulation of the natural electromagnetic environment. This field doesn't cause earthquakes. Remember, we've established that's physically implausible, but it creates a kind of resonance in Earth's mantle, a subtle standing wave pattern that slightly alters the distribution of stresses in the crust. Not enough to trigger earthquakes where none would occur, but enough to shift the timing slightly to create a pattern. Earthquakes that would have happened anyway, triggered by the relentless motion of tectonic plates, now happen in a slightly different sequence, a slightly different timing pattern. To human seismologists, it looks like a random increase in activity, but to the probe, measuring seismic waves as they ripple through Earth's interior, it's structured data. Each earthquake becomes a data point in a three-dimensional map of Earth's interior structure. The probe isn't harming Earth, it's not killing anyone, not destroying anything. It's simply observing, using Earth's natural processes like a doctor using a stethoscope. The increased earthquake activity we're observing isn't an attack, it's diagnostic imaging. And here's the truly unsettling part. We might not be the first. And this might have happened before in Earth's geological history. Might there be patterns in the paleoseismic record, patterns in ancient earthquake frequency that correlate with cometary visits? We've never looked for such patterns because we've never had reason to suspect they might exist. What if interstellar probes have been visiting Earth for millions of years? What if every few 100,000 years one passes through, conducts its survey, and moves on? What if there's a catalogue somewhere, not here, not accessible to us, but somewhere in the galaxy, containing detailed information about Earth's interior structure, its atmosphere composition, its biosphere diversity, its geological evolution? What if we're not alone in the universe, but we're also not significant enough to warrant direct contact? What if we're specimens catalogued and filed away, interesting enough to study, but not interesting enough to engage with? This is the existential horror at the heart of the worst-case scenario. Not destruction. We've established 3i Atlas poses no physical threat, not even hostile intent. There's no reason to believe any hypothetical probe would wish us harm. No, the horror is irrelevance. The horror is being studied like bacteria in a petri dish, observed by intelligences so far beyond us that they don't even consider us worthy of communication. The horror is knowing that everything we are, our civilizations, our art, our science, our struggles, might be nothing more than data points in someone else's star catalogue. Dr. Robert Harrison, a philosopher of science at Oxford, explored this idea in a controversial paper. The catalogued Earth hypothesis. He writes, if we are being observed by advanced extraterrestrial intelligence, the most likely scenario is not invasion or contact, but passive observation. We may be one of millions of planets being surveyed, catalogued, and filed away. The psychological impact of discovering such observation might be more devastating than any physical threat. Because here's what would change: nothing and everything. Earth would continue spinning. tectonic plates would continue moving, humans would continue living their lives, but the cosmic context would shift fundamentally. We would know we're not alone, we would know we're being watched, and we would know there's absolutely nothing we could do about it. We couldn't communicate with the probe, it's too advanced, operating on principles we don't understand. We couldn't stop it. What would we do? Send a rocket to a comet traveling at 94 kilometers per second, 185 million kilometers away? We couldn't even prove it was there, not definitively, because it's designed to look natural. We would live with the uncertainty forever. Every unusual astronomical object would carry the question, is it natural or is it them? Every unexplained seismic pattern would whisper, is it geology or is it diagnostic scanning? The worst case isn't destruction, it's knowledge without understanding, it's confirmation that we're not alone, coupled with the realization that we don't matter enough for contact. It's being the ant farm on some cosmic researcher's desk, alive, active, complex in our own way, but ultimately just an experiment being observed from beyond our comprehension. And if this is happening now, if 3i Atlas really is a probe conducting a survey, then what? Do we panic? Do we celebrate? Do we try to communicate knowing we probably can't? Do we shut down our radio telescopes and hide? Or do we broadcast louder than ever? What does humanity do when it discovers it's been catalogued? This is speculative fiction masquerading as hypothesis, I know. The probability that any of this is true is vanishingly small. The null hypothesis, natural comet, coincidental timing, remains overwhelmingly more likely. But the thought experiment serves a purpose. It shows us what genuine worst case looks like. Not Hollywood destruction, not physics-defying disasters, but the quiet, unsettling realization that we might be profoundly less important than we imagine ourselves to be. Arthur C. Clarke wrote, "Two possibilities exist. Either we are alone in the universe, or we are not. Both are equally terrifying." The worst-case scenario isn't about which possibility is true. It's about discovering the truth in a way that leaves us powerless to do anything about it. If 3i Atlas is a probe, if we're being studied, if there's a catalogue somewhere containing information about our planet that we ourselves have barely managed to gather, then the universe is stranger and more populated than we dreamed, and we're smaller and less significant than we feared. That's the worst case. Not death, but irrelevance. Not destruction, but disregard. Fortunately, it's almost certainly not true. Almost certainly, 3i Atlas is just a comet, the earthquakes are just geology, and the correlation is just coincidence. Almost certainly. But to understand why this speculation arose in the first place, we need to look at the broader context of our search for life in the universe and the profound questions that search raises. To understand why some scientists entertain exotic hypotheses about interstellar visitors, we need to grapple with one of the most profound puzzles in all of science, the Fermi paradox. The paradox is named after physicist Enrico Fermi, who reportedly asked during a lunch conversation in 1950, "Where is everybody?" Where is? The logic is simple but devastating. The Milky Way galaxy contains roughly 200 to 400 billion stars. Many of those stars have planetary systems. Some of those planets are in the habitable zone, the orbital distance where liquid water can exist on a planet's surface. Life on Earth arose relatively quickly after the planet cooled enough to support it. If life is common, and if some tiny fraction of life-bearing planets develop intelligent civilizations, and if some of those civilizations develop spacefaring technology, then statistically we should see evidence of them everywhere. Even without faster-than-light travel, a civilization could colonize the entire galaxy in a few million years using generation ships or self-replicating probes. The galaxy is 13.6 billion years old. There has been plenty of time for multiple civilizations to arise, expand, and leave evidence of their existence. And yet we see nothing. We detect no artificial megastructures around distant stars. We receive no radio signals that couldn't be explained by natural phenomena. We find no artifacts in our solar system, no signs of industrial activity, no evidence whatsoever that intelligence exists anywhere but Earth. This is the Fermi paradox, the apparent contradiction between the high probability of extraterrestrial civilizations and the complete absence of evidence for them. Many solutions have been proposed. The rare Earth hypothesis suggests that while simple life might be common, complex multicellular life requires such a precise set of conditions that it's extraordinarily rare. Earth might be one of only a handful of planets in the galaxy that developed complex ecosystems. The Great Filter proposes that there's some barrier in the evolution from chemistry to spacefaring civilization that's extremely difficult to pass. Perhaps most planets never develop life. Perhaps most life never develops intelligence. Perhaps most intelligent species destroy themselves before achieving interstellar travel. The terrifying question is the Great Filter behind us or ahead of us? The zoo hypothesis suggests that advanced civilizations know about us but deliberately avoid contact, either to let us develop naturally or because they follow some kind of non-interference directive. We're the wildlife preserve, observed but not contacted. The dark forest hypothesis, popularized by Liu Cixin's science fiction novel, proposes something more sinister. Civilizations hide because the universe is dangerous. Any civilization that reveals itself might be destroyed by older, more powerful civilizations. Everyone stays quiet, everyone hides, creating the illusion of emptiness. Each solution to the Fermi paradox is unsettling in its own way. If we're rare, we're terrifyingly alone. If there's a Great Filter ahead, we might be doomed. If we're being observed but ignored, we're cosmically insignificant. If civilizations hide in fear, the universe is more dangerous than we imagine. This context explains why some scientists take hypotheses about probes seriously. If the zoo hypothesis is correct, if we are being observed, then we should expect to find subtle signs, objects that seem natural but aren't, patterns that seem random but contain information, surveillance that's careful enough to avoid obvious detection. Dr. James Benford, a physicist who has written extensively about interstellar probes, argues, if we're looking for extraterrestrial intelligence, we should look for what we would do. We would send probes. We would disguise them to avoid contaminating observations. We would make them small and efficient. And we would expect other civilizations to do the same. SETI has spent decades listening for radio signals. Perhaps we should spend more time looking for physical artifacts. This line of thinking has led to serious proposals for searching our solar system for lurkers, hypothetical probes that might be observing us from co-orbital positions with asteroids or from stable orbits where they'd remain hidden. The concept isn't as fringe as it might sound. In 2018, a paper published in the Astronomical Journal by James Benford and his brother Gregory argued that near-Earth asteroids would be ideal locations for surveillance probes. They're stable, they require no energy to maintain position, and they're close enough to Earth for detailed observation. The paper proposed that we systematically survey near-Earth asteroids with radar looking for anomalies, objects that reflect radar in unexpected ways, or that show geometric shapes inconsistent with natural formation. So far, no such surveys have found anything suspicious. The asteroids we've examined in detail appear to be exactly what they seem, rocks tumbling through space, shaped by impacts and the slow erosion of solar radiation. But we've examined only a tiny fraction of the objects in our solar system, and if a probe wanted to remain hidden, disguised as a natural comet or asteroid, we might not recognize it unless it wanted to be recognized. This brings us back to 3I Atlas. If the universe contains civilizations and they send probes, and if those probes are designed to be unobtrusive, what would we expect to see? We'd expect objects that look natural, comets, asteroids. We'd expect them to follow mostly natural trajectories, with only subtle anomalies that could be explained away. We'd expect them to activate only when observing something interesting, remaining dormant the rest of the time. And we'd expect the vast majority to pass through unnoticed, with only occasional objects sparking speculation when they show slightly unusual characteristics. In other words, we'd expect exactly what we're seeing. This doesn't mean 3i Atlas is a probe. The null hypothesis remains far more likely, but it does mean that dismissing the possibility out of hand might be premature. If we're truly scientific in our thinking, we should remain open to all hypotheses, weighting them appropriately by probability but not refusing to consider them. The Fermi paradox haunts these discussions. Where is everybody? If they're out there, why haven't we found definitive proof? If they're not out there, why are we so statistically unlikely to be alone? Maybe 3i Atlas is part of the answer. Maybe the silence isn't because they're not there. Maybe it's because they're being very, very quiet. Maybe they're watching, cataloguing, studying us from disguised platforms that we mistake for natural objects. Or maybe we really are alone, and every unusual comet is just a comet, and the universe is vast and empty except for us. Both possibilities are terrifying. Both possibilities might be true. And 3i Atlas, regardless of what it actually is, forces us to confront these cosmic questions. What would we do if we knew for certain? How would we respond? Here's an uncomfortable truth. Humanity has no unified plan for what to do if we detect definitive evidence of extraterrestrial intelligence. We have rough protocols scattered across various institutions. The International Academy of Astronautics has a Declaration of Principles Concerning Activities following the detection of extraterrestrial intelligence, last updated in 2010. It's a well-meaning document that outlines steps for verification, announcement, and international cooperation. But it's not binding, it has no enforcement mechanism, and it was written with Radio SETI in mind, the scenario where we detect a signal from a distant star system, giving us time to verify and respond carefully. Nobody seriously planned for the scenario of a physical object already in our solar system that might be artificial. If 3i Atlas were confirmed to be a probe, and to be absolutely clear, it almost certainly isn't, what would happen? The discovery would likely unfold in stages. First, astronomers would notice definitive anomalies in the data, perhaps radio emissions that couldn't be natural, or geometric structures visible in high-resolution images, or course corrections that definitively ruled out outgassing. Initially, the discovery would be kept quiet while scientists verified their findings. This isn't conspiracy, it's standard scientific procedure. You don't announce extraordinary claims without extraordinary verification. But secrecy wouldn't last long. Too many observatories, too many amateur astronomers, too many independent researchers have access to the data. Within days or weeks, the information would leak. Social media would explode with speculation. Governments would be forced to respond before they were ready. Dr. Stephen Dick, former NASA chief historian, explored this scenario in his book, Astrobiology, Discovery, and Societal Impact. First contact would be chaotic. Despite decades of speculation and planning, the reality would likely overwhelm our prepared responses. We would face immediate questions. Who speaks for Earth? How do we communicate? What do we say? Do we attempt to interact with the probe or leave it alone? Different nations would have different priorities. Some might see the probe as a threat and advocate for attempting to disable or destroy it. Others might see it as an invaluable opportunity for scientific study. Religious institutions would grapple with theological implications. The public would divide between those excited by the discovery and those terrified by it. The economic impacts could be severe. Stock markets might crash on the news. Religious fundamentalism might surge. Governments might face legitimacy crises as people questioned why they weren't told sooner, or accused authorities of hiding information. Dr. Michael Michaud, in his book Contact with Alien Civilizations, argues, the detection of extraterrestrial intelligence would be the most profound event in human history. It would permanently alter our self-conception our understanding of our place in the universe and potentially our social structures. We like to imagine we'd react rationally, but history suggests otherwise. There's a darker possibility too. If 3i Atlas were confirmed as artificial and if its purpose were unclear, some nations might interpret it as a reconnaissance mission preceding invasion. The probe might be destroyed out of fear, eliminating our only chance to learn from it. This isn't paranoid speculation, it's based on how humans have historically responded to encounters with more advanced civilizations. When European explorers reached the Americas, the contact was catastrophic for indigenous peoples. When technologically advanced societies encounter less advanced ones, the outcomes are rarely positive for the less advanced. We're the less advanced ones in this scenario. Dr. Seth Shostak from the SETI Institute tries to be reassuring. If an extraterrestrial civilization has mastered interstellar travel, they're likely peaceful. Aggressive civilizations tend to self-destruct before achieving such technology. Any species capable of sending probes across light years has probably evolved beyond primitive violence. Maybe. But that's an assumption based on human psychology projected onto completely alien minds. We have no idea how extraterrestrial intelligence might think, what it might value, what it might want. The United Nations Office for Outer Space Affairs, UNOSA, would theoretically coordinate international response, but it has limited authority and even less enforcement power. In practice, response would be fragmented with major space powers, the United States, China, Russia, Europe, each pursuing their own agendas while attempting to maintain a facade of cooperation. The scientific community would scramble to learn everything possible. Telescopes worldwide would focus on 3i Atlas. Radio dishes would scan for signals. Missions would be hastily planned, perhaps a flyby probe launched on a fast trajectory to rendezvous with the object before it left the inner solar system. But all of this assumes rational response to confirmed evidence. What about the scenario we're actually in, where the evidence is ambiguous, where most scientists think 3i Atlas is natural, where only a few researchers are suggesting it might be artificial? In that scenario, we do nothing. The object is studied as a natural phenomenon. Papers are published. Data is archived. 3i Atlas completes its passage through the solar system and returns to interstellar space. And humanity continues on, never knowing for certain what it was. Maybe that's the right approach. Maybe with ambiguous evidence, caution is warranted. Maybe the disruption that would follow from prematurely announcing we might be being observed would cause more harm than good. Or maybe we're missing the most important discovery in human history because we're too cautious, too invested in the null hypothesis, too afraid of being wrong. Dr. Jill Tarter, former director of the SETI Institute, offers perhaps the wisest perspective. We prepare by doing good science. We observe, we measure, we analyze. We don't jump to conclusions, but we don't dismiss possibilities. If contact comes, it will come through data, through evidence that compels even skeptics to reconsider. Until then, we watch, we wait, and we wonder. That's where we are with 3i Atlas. Watching, waiting, wondering, hoping the answer, whatever it is one we're ready to hear. But ready or not, the universe doesn't wait for our permission to reveal its secrets. Let's engage in a thought experiment. Let's assume, just for the sake of argument, that the speculative scenario is real. 3i Atlas is a probe. It's conducting a geological survey of Earth using seismic activity as diagnostic data. We've confirmed this with definitive evidence, perhaps by detecting artificial radio emissions, or by observing clear course corrections, or by capturing high-resolution images that show geometric structures inconsistent with natural formation. What happens next? The first response would be verification. Multiple institutions would need to confirm the findings independently. You can't announce the most profound discovery in human history based on data from a single observatory. NASA, ESA, Roscosmos, CNSA, and dozens of university observatories would turn their instruments toward 3-Eye Atlas. Within weeks, perhaps days, the evidence would be overwhelming. 3-Eye Atlas is artificial. Humanity is not alone. We are being observed. The President of the United States would likely convene an emergency meeting of the National Security Council. Similar meetings would occur simultaneously in Beijing, Moscow, Brussels, New Delhi. The UN Security Council would be called into emergency session. The immediate question: is this a threat? Military analysts would assess capabilities. 3-Eye Atlas hasn't done anything obviously hostile. It hasn't fired weapons, hasn't approached Earth closely, hasn't attempted to land or extract resources. Its apparent mission, surveying Earth's geology, doesn't suggest hostile intent. But intentions can change. Orders can come from wherever 3-Eye Atlas originated. The probe might be a precursor to something else: colonization, resource extraction, or worse. Defense departments would scramble to develop response options. Could we destroy 3-Eye Atlas if we needed to? Probably not at its current distance and velocity, but maybe. A kinetic impactor launched on an intercept trajectory might reach it, though targeting something moving at 94 kilometers per second would be extraordinarily difficult. Should we destroy it? That debate would rage immediately. Scientists would argue vehemently against destroying what might be our only opportunity to learn from an advanced civilization. Military strategists would counter that we can't risk letting a potential threat remain functional. Diplomats would worry about the message destruction would send. What if other probes are watching? What if destroying this one triggers a hostile response? While debate raged, the public would be losing their minds. The announcement, and there would have to be an announcement, you can't keep evidence this definitive secret for long, would trigger reactions ranging from euphoria to terror. Religious communities would grapple with theological implications. Does extraterrestrial intelligence contradict religious doctrine? Different faiths would answer differently. The Vatican, which has historically been surprisingly open to the possibility of alien life, might adapt relatively smoothly. More fundamentalist traditions might face crisis. Financial markets would experience severe volatility. On one hand, confirmation of advanced technology might spark hopes for revolutionary discoveries, new physics, new energy sources, new materials. On the other hand, uncertainty is the enemy of markets, and this would be the ultimate uncertainty. Think about the volume of space we're discussing. The solar system, defined as the region of the Sun's gravitational dominance, extends roughly 100,000 astronomical units, or about 1.5 light-years. That's a sphere with a volume of approximately 14 cubic light-years. Even if every star in the galaxy had sent out 1,000 probes over billions of years, and even if those probes explored for millions of years each, the density of probes at any given moment would be incredibly low. The probability that one would pass through our specific stellar system during the brief window of human technological civilization is vanishingly small. And yet here we are, watching 3-Eye Atlas, wondering. Dr. Frank Drake, creator of the famous Drake equation for estimating the number of communicating civilizations in the galaxy, once noted, "The absence of evidence is not evidence of absence. The universe might be full of life, but finding it requires looking in the right places at the right times with the right methods. We've barely begun to search." Humanity's radio signals have been radiating into space for about a century, traveling outward at the speed of light. That means our broadcasts have reached stars within a 100 light-year radius, a tiny bubble in the vastness of the galaxy. Anyone looking at Earth from more than 100 light-years away wouldn't even know we're here yet. Our presence hasn't had time to propagate. Conversely, if civilizations exist within that 100 light-year bubble and they're listening, they might have detected our presence recently. They might be watching us now, observing the strange electromagnetic signatures of a newly technological species. 3-Eye Atlas, if it came from a star system in that region, might be a response to our radio broadcasts. A probe sent to investigate after detecting our signals, arriving now because the journey takes time, even at relativistic speeds. Or it might have nothing to do with us at all. It might be one of countless probes mindlessly executing surveys programmed billions of years ago, long before humans existed, perhaps before Earth itself existed. Or, most likely, it's just a comet, a frozen remnant from another star's planetary formation process, ejected into interstellar space by gravitational perturbations, wandering the galaxy for eons before happening to pass through our neighborhood. No intelligence, no purpose, no meaning, just a rock. The scale of the cosmos makes both possibilities seem equally improbable and equally possible. The universe is so vast that extraordinary coincidences must occur constantly, and yet so old that extraordinary purposeful actions have had ample time to unfold. We're left with uncertainty, humility, and wonder. The cosmic perspective doesn't answer our questions about Three-Eye Atlas. It simply frames them against a canvas so vast that our questions themselves seem both critically important and cosmically insignificant. Both can be true. We matter, and we're tiny. Our moment is precious, and it's fleeting. The universe might be full of life, or we might be heartbreakingly alone. Three-Eye Atlas, whatever it is, reminds us of these truths. Amid all the speculation and uncertainty, let's take stock of what we've actually accomplished. Because regardless of whether Three-Eye Atlas is a natural comet or something more exotic, its passage through our solar system has been a triumph of human science and cooperation. Think about what we've achieved. A visitor from another star system, only the third ever confirmed, entered our solar system and we detected it. We tracked its trajectory with precision. We analyzed its composition using spectroscopy. We coordinated observations across multiple continents, multiple institutions, multiple nations. We've gathered data that will inform our understanding of cometary formation, interstellar chemistry, and the dynamics of our cosmic neighborhood for decades to come. This wasn't inevitable. Oumuamua nearly escaped detection entirely. We spotted it only after it had already begun its outbound journey, and we were lucky to catch it at all. The Atlas survey system that detected Three-Eye Atlas represents years of work, millions of dollars of investment, and the dedication of astronomers who spend countless nights scanning the skies for objects that might threaten Earth or simply expand our knowledge. Dr. Jennifer Hayes, principal investigator for the Atlas project, reflected on the detection. Three-Eye Atlas validates everything we've built this system to do. We found an unprecedented object, tracked it accurately, and shared the data globally within hours. This is science working exactly as it should, transparent, collaborative, rigorous. The international cooperation has been remarkable. Data from the Hubble Space Telescope, the James Webb Space Telescope, the European Southern Observatory's Very Large Telescope, China's Sky-Eye Radio Telescope, and dozens of smaller observatories has been shared openly. Scientists from nations that sometimes struggle to cooperate politically have worked together seamlessly to study this object. That alone is cause for hope. If we can cooperate on studying an interstellar comet, perhaps we can cooperate on the far more pressing challenges we face on our own planet: climate change, pandemic preparedness, nuclear non-proliferation. The cosmic perspective can unite us if we let it. We've also seen tremendous public engagement. Amateur astronomers around the world have contributed observations. Citizen scientists have helped analyze data. Online communities have formed to discuss findings, share images, and explore implications. Science communication channels, like this one, have translated complex research into accessible content, allowing millions of people to participate vicariously in the discovery process. This democratization of knowledge is unprecedented in human history. Centuries ago, astronomical discoveries were confined to elite circles, accessible only to those with expensive equipment and specialized training. Now anyone with internet access can view the same images professional astronomers analyze. Anyone can read research papers, run orbital simulations, engage with the science. Dr. Neil deGrasse Tyson commented on this phenomenon. We're living in a golden age of astronomical discovery and public engagement. People aren't just passive consumers of science, they're active participants. That engagement creates a scientifically literate public capable of making informed decisions about everything from space exploration funding to planetary defense priorities. The data itself is remarkable. Spectroscopic analysis has revealed chemical compositions never before seen in solar system objects. Complex organic molecules, exotic ice formations, mineral structures that tell stories about the environments where 3I Atlas formed. Each discovery adds to our understanding of how planetary systems form and evolve. We've learned that interstellar space isn't quite as empty as we once thought. The detection rate of interstellar objects, 3 in just 8 years, suggests that such visitors might be relatively common. With better detection systems coming online, we might spot dozens or even hundreds in the coming decades. This has profound implications for planetary defense. If interstellar objects pass through regularly, we need systems to detect them early, characterize their orbits precisely, and assess any potential threats. The infrastructure we're building, survey telescopes, rapid response protocols, international coordination mechanisms, serves double duty, advancing pure science while also protecting Earth from potential impacts. The seismic activity that initially sparked speculation has also taught us valuable lessons. Seismologists have taken the opportunity to examine earthquake patterns in unprecedented detail, looking for any correlations that might reveal unknown triggering mechanisms. While the consensus remains that 3I Atlas has no influence on Earth's geology, the investigation process has refined our understanding of what does influence earthquake timing, tidal forces, atmospheric pressure changes, groundwater variations, and other subtle factors. Dr. Sarah Chen, who's, quote, opened this investigation, later added, "The 3I Atlas correlation forced us to examine our assumptions rigorously. We found no connection, but the process of looking improved our methods and our understanding. That's how science advances, by investigating even unlikely hypotheses and learning from what we find." There's also been unexpected progress in the search for extraterrestrial intelligence. The attention 3I Atlas received has reinvigorated public interest in SETI and related programs. Funding has increased. New detection strategies are being developed. The idea that we should search not just for radio signals but also for physical artifacts, techno-signatures in our own solar system, has gained mainstream acceptance. Dr. Jason Wright from Penn State's Center for Exoplanets and Habitable Worlds leads a program systematically searching for such artifacts. Whether or not 3I Atlas is artificial, it's reminded us that our solar system might contain evidence of extraterrestrial technology. We should look, not because we expect to find anything, the probability is low, but because if something is there, the discovery would be so profound that even a small probability justifies the search. This represents a maturation of human perspective. We're no longer asking only, is anyone out there? We're asking, could anyone have visited here? That's a subtle but important shift, from passive listening to active searching, from assuming isolation to considering alternatives. The educational impact has been enormous too. Schools around the world have used 3I Atlas as a teaching opportunity. Students have learned about orbital mechanics, spectroscopy, the scientific method, and international cooperation. For many young people, this has been their introduction to astronomy and space science, an introduction that might inspire the next generation of researchers. Maya Patel, a high school teacher in London, shared, "My students have been captivated by 3I Atlas. They've learned to read scientific papers, analyze data, think critically about evidence and speculation. They've had discussions about humanity's place in the universe that I've never seen teenagers engage with so thoughtfully. Whether or not there's anything unusual about this comet, it's sparked extraordinary learning. And perhaps most importantly, 3I Atlas has given us something increasingly rare in modern times, a shared experience of wonder. In an era of fragmentation and polarization, Millions of people around the world have looked up at the same sky, wondered about the same object, grappled with the same cosmic questions. That shared wonder is precious. It reminds us of our common humanity, our shared curiosity, our collective vulnerability in a vast and ancient universe. It reminds us that beneath all our differences, we're the same species on the same planet, asking the same fundamental questions about where we came from and whether we're alone. 3i Atlas has given us data, yes, but it's also given us perspective. And in a universe as strange as ours has proven to be, perspective might be the most valuable gift of all. Understanding how we detected 3i Atlas helps illuminate both how much we've accomplished and how much we still have to learn. The detection itself represents a triumph of modern astronomical infrastructure, but it also reveals the limitations we're working within. The ATLAS, Asteroid Terrestrial Impact Last Alert System, consists of 4 telescopes spread across 2 Hawaiian islands and Chile. Each telescope scans the entire visible sky every 2 nights, comparing new images with reference images to detect anything that moves or changes brightness. The system was designed primarily for planetary defense, detecting asteroids that might pose impact threats to Earth. ATLAS operates automatically. Computer algorithms process images, identify moving objects, calculate preliminary orbits, and flag anything unusual for human review. On the night 3i Atlas was first detected, the system registered a moving point of light in an image, compared it with previous observations, calculated its trajectory, and immediately recognized something extraordinary. The object was moving on a hyperbolic orbit. In orbital mechanics, there are 3 types of orbits. Elliptical orbits are closed loops, objects like planets and most comets that remain gravitationally bound to the Sun. Parabolic orbits represent the boundary case between bound and unbound. Hyperbolic orbits are open curves. The object approaches the Sun, swings past it, and continues outward, never to return. Most comets follow elliptical orbits. They might take decades or centuries to complete one orbit, but they're bound to the solar system. A hyperbolic orbit indicates an object with sufficient velocity to escape the Sun's gravity, which means it either came from elsewhere or was accelerated by a close planetary encounter. 3i Atlas showed no sign of having encountered Jupiter or Saturn, the only planets massive enough to accelerate an object to escape velocity. That left one conclusion: it came from interstellar space. This triggered immediate follow-up observations. Within 24 hours, major observatories worldwide were imaging 3i Atlas, confirming the trajectory and gathering spectroscopic data. The object was designated 3i Atlas. The I stands for interstellar, the number indicating it's the 3rd such object confirmed, and Atlas honoring the survey that discovered it. Spectroscopy is how we determine composition. When light from an object passes through a prism or diffraction grating, it splits into component wavelengths, a spectrum. Different chemical elements and compounds absorb or emit light at specific wavelengths, creating a unique signature. By analyzing 3i Atlas's spectrum, astronomers could identify the materials on its surface. Water ice, carbon dioxide ice, carbon monoxide, methane, complex organic molecules. Each leaves its fingerprint in the spectrum. By comparing these signatures to those of solar system comets, researchers could determine what's familiar and what's unusual. The unusual aspects are what sparked the intense scientific interest. 3i Atlas shows spectral features that don't quite match typical solar system comets. Certain molecular abundances are off. The ratio of isotopes, different versions of the same element with different numbers of neutrons, doesn't match what we expect from material formed in our solar nebula. These differences tell us 3i Atlas formed in a different environment, around a different star, under different conditions. That's valuable scientific information about the diversity of planetary systems. It's also, to some minds, slightly suggestive of something more. Dr. Amir Siraj from Harvard explains, natural comets formed in other stellar systems should show chemical differences from solar system comets. That's expected. But the specific differences we're seeing in 3I Atlas are unusual enough to warrant careful study. We're not claiming anything extraordinary. We're simply noting that this object doesn't fit neatly into existing categories. Beyond spectroscopy, researchers have conducted radar observations. Radio telescopes can beam radar signals toward objects and measure the reflections. The strength and character of the reflection reveals information about size, shape, rotation rate, and surface properties. Radar observations of 3I Atlas have been challenging due to its distance and velocity, but preliminary data suggests a roughly spherical or slightly elongated shape, approximately 5 to 8 kilometers in diameter. The surface appears to have moderate reflectivity, consistent with ice and dust. The rotation period is remarkably stable at about 12.7 hours, tidier than most comets, but not inexplicably so. High-resolution imaging from the Hubble and James Webb Space Telescopes has provided visual details. 3I Atlas appears as a fuzzy blob, the nucleus surrounded by a coma of sublimating gas and dust. The coma extends tens of thousands of kilometers. The tail, visible in long exposure images, streams behind the nucleus for millions of kilometers. Nothing in these images suggests anything artificial. No geometric shapes, no obvious structures, no lights or signals. If 3I Atlas were a disguised probe, the disguise would be remarkably thorough. That's the frustrating and fascinating reality of astronomical observation. We can learn a great deal about distant objects, but we're limited by distance and technology. We can measure composition, trajectory, size, and rotation. We cannot see surface details smaller than a few hundred meters. We cannot detect internal structure. We cannot distinguish between a natural comet and a hypothetical probe designed to look natural. Future observations might provide more clarity. As 3I Atlas approaches perihelion, its closest point to the Sun, it will heat up and outgassing will increase. This might reveal additional information about composition and internal structure. If the object fragments, as many comets do when heated, we'd see the interior. If it remains intact and shows unusual resistance to heating, that would be interesting. The European Space Agency has proposed a rapid response interstellar object mission, a spacecraft on standby that could be quickly redirected to intercept and study any interstellar visitor. Such a mission could get close-up images, sample the coma, perhaps even land instruments on the surface. But funding and approval are uncertain, and by the time any mission could reach 3I Atlas, it will likely be too far away. So we work with what we have: telescopes, spectrographs, radar systems, and extraordinarily clever scientists analyzing every photon of data. We extract maximum information from minimum observations, and we live with uncertainty because the universe doesn't always provide the answers we want when we want them. The science of detection is advancing rapidly. Future survey systems will be more sensitive, faster, more comprehensive. We'll detect more interstellar objects, study them in greater detail, and slowly build up our understanding of what's normal and what's not. And maybe someday, one of those objects will be definitively, undeniably, extraordinarily unusual. Until then, we keep watching, measuring, and wondering.